Hello, I'm David Urban, the portfolio scientist for fluid physics, complex fluids, and microgravity combustion at the NASA Glenn Research Center. And I'd like to talk to you today about a concept we're developing for a conversion of the NASA Zero Gravity facility to what we call an ElectroMotive Drop Tower, where we replace the current system with a linear synchronous motor system. Basically, the concept is the current drop facility, which you see pictured on the left, which consists of the vacuum dome and the tube below and the payload here, would all be removed and replaced by a system where the payload rides on a system of rails driven by linear synchronous motors, providing, again, up to 10 seconds of either the gravity level of your choice and much more rapid turnover in the day. Why do we think we should upgrade zero-G? The partial gravity capability is essential for developing and demonstrating technologies for future mission and for fundamental studies, where we can look at gravity as a continuum. And the increased capacity would be provided by this facility, so we'd have this increased throughput and easy access is needed to enable technology verification for future missions and to enable expansion of our fundamental research. We believe that the innovation would be enhanced by this ripping away of the obstacles of flexible testing and variable gravity, and will enable new discoveries that have been stifled by challenges in reduced gravity testing. Why should we do this? Looking forward, NASA plans more aggressive missions, including long-term habitation at partial gravity, prolonged exposure of crew members to low gravity, and sampling on asteroids and comets. And there are also plans moving forward to substantially increase our fundamental research portfolio, which is the topic of this decadal review. And no repeatable, readily accessible partial gravity platform exists for design and validation of these future systems. And this opportunity will provide a revolutionary capability in testing at low and partial G that would overturn current approaches to the study of gravitational effects. Imagine access to the gravity level of your choice for the cost of about 28 bucks a second. This would be very affordable even on outside research grants. And imagine again the ability to do a dozen or more 10-second tests in a single day. And imagine that the launch and capture accelerations you experience by your payload are limited to 6G or even less, allowing experiments that are sensitive to G levels to be easily accomplished. And imagine the ability to control the profile of the transition from the high G acceleration to the low G float modes, again, enabling certain research where the condition of the experiment before the transition to low G is essential. If we are successful in this upgrade, access to low gravity will be changed forever. Why does cost matter? Traditional high-cost access to zero-G has limited use by other disciplines and outside investigators. For example, looking at the utilization of the Bremen Drop Tower, where the program covers the cost, suggests a different outcome with a lower cost point. And this is the utilization from 1990 to the present. You can see in the NASA zero-G facility, it's predominantly combustion testing, which is all locally based researchers, and very limited testing in other disciplines. Partly this is due to the challenges of the timescales of the different experiments, but really, as you look at the Bremen Drop Tower, you see it's also due to other things. Where the Bremen Drop Tower, only a quarter of the utilization is combustion. They have nearly the same amount in fundamental physics and fluid dynamics, with substantial activity in astrophysics, material science, and biology. So it's clear that if the cost point becomes not the barrier, the much broader use of the facility could be expected. To give you an idea of what planetary systems we can accommodate with this our design, our target for G level, partial G, is 1/10th of a G, and that covers a lot of moons and asteroids down to Hygienia. So there's a broad range of bodies in our solar system whose G levels we can simulate. The impact of the upgrade. The biggest change will be, one of the biggest changes will be test turnaround time, which we expect will be dramatically reduced, allowing up to 20 drops a day. Really the big limitation on this is going to be heating of the electromagnetic system due to the thermal loads. And that we will know better after we do the engineering model study, but clearly 20 drops a day is completely feasible. There's certain disciplines where a high rep rate would be desirable, and we're hoping to increase that even further. Partial gravity is essentially not available elsewhere in a regular basis. And this would provide that access would support exploration and study also of gravity as a continuum. What other major impacts would be because of the design and the removal of the need to evacuate the tank each time you do a test. The estimated drop cost would drop from about $3,000 a test to a predicted $263 a test, which is more than an order of magnitude improvement. The lower cost and fast turnaround would invigorate the ground-based programs and also open the facility to make it more accessible to outside users, specifically other scientific agencies and space hardware developers. So a little more on our concept. The pictured on the left is the current facility with the above ground building and high bay, and then below ground you see the shaft with the vacuum chamber within it and all the decelerating systems, etc. All that would be removed except for the concrete walls, and so everything with an X would be removed, and ultimately we'd expect to decommission our 2-second drop tower. What would be replaced would be the electromagnetic rails, power system, ultracapacitor banks, and a new elevator and the drop vehicle itself. We expect substantial improvements where the microgravity level would go from 5 to 10 seconds, utilization going up by an order of magnitude, and also the variable partial gravity capability, and the limiting the decelerations and accelerations to experienced by the payload to a maximum of 6G. Picture to the top right, you see the existing facility with the pressure dome, a vacuum dome, and all that would be removed, allowing ground floor loading instead of having a crane operation to start your experiment. And we'd also have a new elevator shaft for the human access to the lower levels. So the payload would ride down the track at arbitrary speed, launch at getting to 100 miles an hour, and then flying up the trajectory, and then come back down, and then decelerate from 100 miles an hour back to 0. And then ride the elevator back up to be removed as needed. Some payloads would not need to ride up to be turned around, and it could be managed automatically from below. So the overall design, this is a early design. There have been some changes, but the principles are the same. We have a rail system supported where the vehicle rides on wheels and driven by permanent magnets attached to the vehicle in a Hall-Block array, and then electromagnetic system on the stators along the wall. And so the vehicle would ride up and down this rail system driven by the motor system. So you see the overall trajectory. The vehicle would launch from the bottom and accelerate up to 100 miles an hour, and then it would go into the low gravity trajectory where it would ride up and then ride back down over 120 meters each way, taking about 5 seconds each way. And then it would enter the braking zone and brake rapidly in the high power zone over about 30 meters for 1.2 seconds with a peak deceleration of 6G. The way we achieve the ride quality is to have the vehicle fly around the payload via the control system. So within the capsule, we'll have a position sensor which will measure the location of the payload and feed back the information of the control system, which will drive the vehicle to keep the payload centered. For partial G, it's necessary to sit on the floor, so we'll have a damper system to reduce the vibrations from the track and the motors to the payload itself. So, looking forward, I want you to consider what ideas you could propose with given access to this new facility, and how will easy access to 10 seconds of low gravity change your research approach, and what research areas will access to low gravity facilitate. And your white papers on these topics will not only facilitate the construction of this new capability and the overall direction of the microgravity program in general, but they're also an important opportunity to guide us as we define our facility requirements. So we're looking forward to a chance to review the white papers and see if there's additional requirements we need to consider to make best use of the facility. So I thank you for your time, and I hope to see some interesting white papers proposing new concepts for low gravity testing in this facility.